So, welcome to this course of nonlinear vibration. This course is meant for the senior undergraduate and postgraduate students of mechanical engineering department, structural civil engineering department and aerospace engineering department. So, the course structure, the course content is given below. So, it is introduction, development of nonlinear governing equation of motion and analytical solution methods, stability and bifurcation analysis, then numerical techniques. So, total 40 lectures I will spend on this, and module wise the division is like this. So, in the first module it is introduction. So, I will take 3 classes to give brief introduction about this course. In the first class I will tell about this introduction to this nonlinear vibration and linear and nonlinear mechanical vibration, then type of forces, resonances, and I will review the linear vibrating system today. Then next class I will cover this conservative and non-conservative systems, equilibrium points, qualitative analysis, potential well, center, focus, saddle point and cost points. In the third class, so commonly observed nonlinear phenomena like multiple resonance, bifurcation, jump phenomena and different type of periodic, quasi-periodic and chaotic responses. Then in the second module, I will cover this derivation of nonlinear equation of motion. So, there I will take 5 classes. So, in this module I will cover different methods for deriving this equation of motion. So, the different methods include inertia based methods and energy based method. In case of inertia based method, so it is force and moment based approach. So, there I will take the help of Newton's second law or D'Alembert principle to derive the equation of motion, and in case of energy based approach, so Lagrange principle or extended Hamilton principle will be used. And again we will take the single multi degree of freedom system and continuous systems. So, for deriving this equation motion, several case studies we will take to derive these equation motions. Then after deriving the spatio-temporal equation of motion for continuous system or temporal equation for the single, 2 or multi degree of freedom systems, so we will go for finding the solution of the system. In case of continuous system is contains spatio-temporal equation, or initially I will convert that thing to a set of temporal equation by using Galerkin method, and then after deriving the equation motion, the governing equation of motion, so we have to do the ordering using these ordering techniques, and we may use some scaling parameter, bookkeeping parameter, and we will derive the governing equation of motion. So, particularly we will be interested to find the equation of motion of the type Duffing equation, Van der Pol oscillator and Matthew type of equations. So, besides that we may study many other different type of systems. So, in the third module, after deriving this equation of motion, so we have to solve those equation of motion by using some approximate methods. So, in those approximate method we may use this harmonic balance method, or we may go for some perturbation methods. So, before doing this harmonic balance method, so we will do this straightforward expansion and we will see what is the defect in this straightforward expansion method. Also using this harmonic balance method, so we will see that by using very higher order harmonics, so computationally solving this equation of motion will not be proper. So, then we will go for this perturbation analysis, where I will tell you about the Lindstedt-Poincare method, method of averaging, then method of multiple scales, method of normal forms, incremental harmonic balance method, modified Lindstedt-Poincare method and several recently developed methods. So, after deriving this equation and by using these analytical or perturbation methods, so we will convert our ordinary second order differential equation motion to a set of first order differential equation of motion. So, for steady state solution, so we can find a set of algebraic equations, so which we can numerically solve to find the response of the system. Then we will be interested to see the equilibrium, these equilibrium response, equilibrium points and their stability. So, after finding the responses, we will be interested to study the stability and bifurcation of the responses. So, generally 3 different types of responses are observed in case of nonlinear systems. So, one is fixed point response, so it may be trivial or non-trivial response, and then periodic response, quasi-periodic response and chaotic response. So, in all these cases we will study the equilibrium points, their stability and the associated bifurcations. So, few classes I will take for stability and bifurcation of the fixed point response. So, there I will tell about the static bifurcation and dynamic bifurcation. So, in case of static bifurcation, you may see supercritical or subcritical pitchfork type bifurcation, saddle node or transcritical bifurcations, and in case of dynamic bifurcation, so you can see the hop bifurcation. So, it may be supercritical or subcritical type. Similar to the fixed point response, so we will have periodic response also. So, in case of periodic response, so we will study the stability of the periodic response by finding the monodromy matrix. Also, we may use the Lyapunov exponent, or we can go for the Poincare section of the response. Then we will see different routes to chaotic responses. So, the different routes include period doubling, intermittency, torus breakdown, attractor merging, and also we will study about the crisis observed in case of the chaotic responses. So, in the 5th module, I will tell you about different numerical techniques. So, here we will study the time response, FFT, frequency response, and as you know, in case of nonlinear system, a multi stable region will observed or multiple solutions are observed. Then I will tell you different techniques to trace different branches of these responses. Then we, as multiple solutions are available, so we will study about the basin of attractions. So, in this basin of attraction we may use different techniques. So, 2 such technique I will tell, that is, one is point to point mapping and second one is cell to cell mapping. So, we will study then Poincare section of fixed point, periodic, quasi-periodic and chaotic responses, Lyapunov exponents and fractal dimensions. So, we will use different numerical tools to find all these responses. So, lastly, I will take around 10 classes to study different applications of the nonlinear systems. So, there we will study about the single degree of freedom system, multi degree of freedom systems and continuous system. So, in all these cases we will study the free and force vibration. So, the equations already I told you may be of the type Doping type, Van der Pol type equations, and in these cases you can see that we will see simple or primary resonances, SOV or superharmonic resonances. Then we may study the parametrically excited systems, so which are of the Matthew-Hill types of equation. So, there we will use the Foucault theory and we can study the instability region, and some cases of internal resonances also will be covered in this course. So, the textbooks referred in this work are particularly by A.H. Nafe and Mook, Nonlinear Oscillations. Then the 4th one is Nafe and Balchandran, Applied Nonlinear Dynamics. Also the other references I will follow, that is Moon, FC Moon and FC Moon, Chaotic and Fractal Dynamics, an introduction for applied scientists and engineers. Then perturbation method by Nafe, then introduction to perturbation techniques by Nafe, then the behavior of nonlinear vibrating system by Wanda Stupnica, introduction to linear, parametric and nonlinear vibrations by Catmull, and practical numerical algorithms for chaotic systems by Parker and Chua. Also, I will give you few examples on the method of normal forms. There I will use the book by A.H. Nafe. So, also we will take the help of many journal papers. So, particularly in this field of nonlinear vibration. So, you can find the journals are very useful. So, the journals include International Journal of Nonlinear Mechanics by Elsevier, Nonlinear Dynamics by Springer, then Journal of Sound and Vibration Elsevier, Journal of Vibration and Acoustics ASME, Journal of Dynamical Systems Measurement and Control by ASME, Physics D, Nonlinear Phenomena Elsevier, Chaos, Soliton and Fractals Elsevier, International Journal of Nonlinear Sciences and Numerical Simulation, and Journal of Computational and Nonlinear Dynamics ASME. So, we will take several case studies from these journal papers and we will study the nonlinear phenomena associated in these systems. So, to start with, let us see some mechanical systems and we will see how the vibration phenomena is occurring in those systems. So, this page shows, so these are some of the gears shown in these slides. So, this is a spur gear. So, you can have spur gear, different types of gears, spur gear, bevel gears, also you may have helical gears. So, this is bevel gear, this is rack and pinion, this is worm gear and this is gear train. When more than 2 gears are used, so it is known as gear train. So, in these cases you can have a linear or nonlinear systems. You can model this rack and pinion or these gear systems by a linear rotary system. For example, in this case of rack and pinion, you can convert this system to a rotary, an equivalent rotary system or an equivalent translatory system. So, if perfect rolling is assumed and if there is no manufacturing defect, so in that case you may neglect the vibration in the system, but due to the presence of manufacturing defect, backlash, clearance, so in these systems most of the times you may see the vibration occurring in these type of systems. So, this is the animation for the steam engine. So, you can see different mechanical parts associated in the steam engine. So, you have a cylinder piston arrangement, then this is the governor. So, the connecting rod, this is the crank is rotating this wheel. So, in this system, in this reciprocating system, so one may observe inherent unbalanced force due to this inertia force associated in the system. So, also due to wear and tear in different mechanical parts, one may observe severe vibrations. This slide shows the internal combustion engine. Here also you can have several parts. So, this is particularly a slider crank mechanism. So, in this slider crank mechanism, one can have this unbalanced primary, secondary or harmonic forces in the direction of line of stroke. Also, you can have different parts like this cam and other different parts which will be subjected to vibration due to this unbalanced force present, inherent unbalanced force present in this system. So, this is a rotary engine, this is Geneva mechanism. So, the animation of these systems are shown here. Starting with these components of different machine parts. So, you can see different machines in this workshop. So, this a lathe machine, this is a radial drilling machine, this is vertical milling machine and this is shaper machine. So, this is a 5-axis robot and this is UTM. So, in all these cases one may observe that the parts are very rigid. So, due to this, to make it rigid or to make it very high stiffness, so one has to use heavy materials or make the components very heavy, but to reduce this weight for different application, for example for space application. So, to reduce the weight, so one has to use light or flexible material. So, in case of flexible or light material, the components will be subjected to vibration. This slide shows the spot welding line. So, here several robots are used to manufacture a job. So, these robotic parts are very rigid. So, it required heavy inertia, and due to heavy inertia one may use high rating prime movers. So, to reduce the inertia one may make it of lightweight. So, to make it lightweight, again the system will be flexible and will be subjected to vibration. So, these vibration one may model it as very small, and that time one may take a linear system. So, but if the vibration is not small, so in those cases one has to consider the system to be nonlinear. So, this slide shows a nuclear reactor. So, in this nuclear reactor, to open the nozzle valve, so one may use a robot, one may do this thing manually or one may use robot, but due to this radioactive nature a robot is preferable, but in that case also lot of vibration will occur if one consider a flexible manipulator. So, this is a patient positioning system. So, in this patient positioning system very accurate positioning is required. So, for this precision positioning system, slight unbalance will cause severe damage to the patient. So, in those cases a nonlinear analysis, or one may reduce the vibration by using nonlinear system analysis. This is also another. So, this is the part of the patient positioning system. So, several parts are shown here. So, one may see these links, if it is not rigid or if it is flexible, then it will be subjected to nonlinear vibration. So, this is a long reach manipulator. So, this part is the long reach manipulator used for repairing purpose in this satellite. So, in spacecraft due to weight constraint, so this long reach arm should be of flexible. So, due to the flexible nature, so they will be subjected to vibration. So, one cannot model this vibration to be small, and in that case one will use the nonlinear vibration approach. Here also a 2-link flexible manipulator is shown, and this is also a 2-link flexible manipulator. So, this is a spine biopsy simulator. So, in this case this needle part who is touching this bone, so it is flexible. So, due to that flexible nature it will be subjected to vibration. So, this is a turbine. So, these blades are shown. So, due to unbalance in this, sometimes unbalance may occur in this turbine blade. So, due to that severe vibration may occur in the system. To avoid those vibration, so nonlinear analysis may be required. Also in these cases, these turbines, nonlinear analysis will be required. So, this is Chandrayaan. So, in this case also one may go for this nonlinear vibration analysis. So, now let us see what are the elementary parts of a vibrating system. Here a very simple harmonic motion of a simple pendulum is shown. The simple pendulum which contain a massless thread with a bob here, it moves given a initial disturbance. So, it moves. the kinetic energy. So, when it is at the topmost position, its velocity is 0. So, kinetic energy is 0. So, all the kinetic energy is converted to potential energy, as now it is coming back to this original position due to restoring force. This restoring force is coming due to gravity. So, the potential energy decreases and it converts to kinetic energy. So, one can see this kinetic energy increase and decrease of kinetic energy. The total energy of the system is constant. So, in this case, to have vibration in this system, so one required a disturbing force, initial disturbing force. Then after the initial disturbing force is applied or the body is kept at this position, due to a restoring force, it comes back to its original position, that is this equilibrium position. But at its original position or at this equilibrium position, as the body has high velocity, so it is subjected to, so at the body has low velocity, at this point the body has high velocity, the velocity decreases, and at this point the body has potential energy, all potential energy, this potential energy is reduced, and here the velocity, all potential energy is converted to kinetic energy. So, velocity is very high. So, at this point due to inertia, the body is moving to opposite direction. Let it has started from this position. So, at this position due to inertia it has moved off. So, here velocity is 0. So, again it will trace back to this original position. So, this oscillation will continue if this experiment is conducted in vacuum, but if it is conducted in any ordinary room, so this vibration will come to, or the pendulum will come to rest after some times. So, due to presence of this air damping, the vibration will be 0 after some times. So, we have seen, so 4 different types of forces are acting in the system. One is the disturbing force, second one is the restoring force, third one is the inertia force, and fourth one is the damping force. So, each force is associated with one type of energy and one system parameter. So, the restoring force is associated with the potential energy. So, in this case of pendulum, so the potential energy is due to the gravity, and then the inertia force. So, inertia force is associated with the kinetic energy. So, due to mass of the system, so it has inertia force. So, inertia force is mass into acceleration, and it acts in a direction opposite to that of the acceleration, and then a means by which energy is lost, that is damping. So, the damping force is associated with a energy loss due to dissipation energy. So, we have 3 different types of energy. So, one is your potential energy, second one is the kinetic energy, and third one is the dissipation energy in the system. So, the elementary parts of the vibrating system associated with the inertia force is mass, associated with the potential energy is the stiffness, and associated with the dissipation energy or damping force is the damper. So, in a system one may use a mass, a stiffness, and a damping element. So, in case of the stiffness, so for example, in this case due to this gravity, so it has gained this potential energy. But if one will take a cantilever beam or a beam, so in that case due to the elasticity of the system, elasticity E of the system, E I of the system, the body will gain this potential energy, or the potential energy will be the strain energy in this case. So, a vibrating system will have a mass, a spring element or a stiffness element, then a damping element. So, this slide show a spring and damper system. So, this is the mass. So, during this vibration, so if it is very small or if the damping and the spring are assumed to be linear, then one can see a linear motion or a simple harmonic motion. So, this slide, this animation shows a simple harmonic motion associated with a spring and mass system. But if the spring stiffness is not linear or if the spring is not linear, so in that case the motion will be different type, and in this course we are going to study what will be the motion if the spring is not a linear spring. So, in this case the soil is modeled as different springs and the associated vibration is shown. So, we may classify the vibration into free or force vibration type. It may be damped or undamped type, linear or non-linear type, then it may be deterministic or random. So, in case of free vibration, after applying a initial unbalanced force or a initial disturbing force, the system is not subjected to any other force. After applying this disturbance force, the system is left without any force and the system will vibrate and come to rest due to damping. Again, this free vibration can be divided into three different categories. So, depending on the damping, so it may be under damped, it may be critically damped or it may be over damped. And in case of force vibration, so depending on the nature of the force, we can have different type of response. So, while the free vibration will give rise to a transient response which will die due to the presence of damping, in case of force vibration the system will oscillate with different amplitude and frequency depending on the nature of the force. The force may be fixed, it may be periodic, it may be a stochastic type of force. So, in case of periodic also the force may be of harmonic type or it may not be of harmonic type. And in case of linear and non-linear systems, so we will divide the system to be linear when it obey the principle of superposition, and when it will not obey the principle of superposition we can define the system to be non-linear. So, today we will see several examples how to distinguish between a linear and non-linear system. Also, so we can have deterministic system, and in case of deterministic, so we may have, in case of deterministic response we may have fixed point response. The response may be periodic, it may be quasi periodic or it may be chaotic, and the force may be a random type of force, the force may be a deterministic type of force also. So, the earthquake force is a random type of force. So, in all these cases to analyze the system we required different coordinate systems. The coordinate system may be a physical coordinate system or it may be a generalized coordinate systems. That thing we will discuss more in second module. So, one may follow 4 different steps for this vibration analysis. So, given a physical system, first one has to find the simplified mathematical model. So, to find the simplified mathematical model one may go for equivalent systems. So, in these equivalent systems one may find equivalent mass, equivalent damping and equivalent stiffness of the system. After making a simplified model, then one has to determine the equation of motion, and after getting the equation of motion, so one has to solve this equation of motion to obtain the response, and this response can be studied for bifurcation stability and bifurcation analysis. After getting those responses and their stability, so one has to interpret these results in terms of the physical system. So, in case of equivalent system, to find the equivalent mass of the system, so one can equate the kinetic energy of the original system with that of the equivalent system. Similarly, to find the equivalent stiffness of the system, the potential energy of the original system should be equated with the potential energy of the equivalent system, and in case of equivalent damping, so one has to equate the dissipation energy of the original system with that of the equivalent system. So, we will see some examples how to find these equivalent mass, stiffness and damping, and to model or to get simplified model. So, one can use this lumped parameter system, one can model the system as a single degree of freedom system, 2 degree of freedom system or multi degree of freedom system, or one can go for a continuous system modeling also. So, in case of single, 2 or multi degree of freedom system, so one will have in case of single degree of freedom system, one will have single differential equation of motion. In case of 2 degree of freedom system, one will have a matrix equation, differential equation in this form, that is m x double dot plus k x plus c x dot equal to f. So, in this mass m is the mass matrix, k is the stiffness matrix, c is the damping matrix, x is the response and f is the force applied to the system. So, f is a vector and x is a vector. So, in case of multi degree of freedom system, so one has to solve this. So, if this is a n degree of freedom system, for example, one can take a 12-story building. So, in that case one can write this M matrix by using a 12:12 element. Similarly, the stiffness and damping matrix can be written with 12:12 elements, and this force will be F vector will be, so it will contain 12 components. So, one can use modal reduction method or modal analysis to convert this equation. So, if this equation, if this mass matrix and stiffness matrix and damping matrix are coupled, then one can use this modal analysis method to convert these equations or to convert this mass matrix, stiffness matrix and damping matrix to a set of uncoupled differential equation of motion. So, in that way, by using modal analysis method, so one can have n number of uncoupled single degree of freedom equation. So, knowing the solution of a single degree of freedom system, so one can find the response of a multi degree of freedom systems also. So, here several examples are given. So, this is only a spring and damper. The equation of motion can be written as k x plus E x dot equal to F. So, this is a first order system. So, in this case this is a spring, mass and damper system. The equation of motion can be written as m x double dot, where x is the displacement of this. So, m x double dot plus k x plus E x dot equal to F. So, this is a second order system. So, in these cases I am assuming the spring to be linear, that is why the spring force or the stiffness force I am writing equal to k x. But if the spring is not linear, then one cannot write the spring force to be k x, and in that case the equation of motion will be nonlinear. So, to find equivalent stiffness, so for example, let us take this crane system. So, in this crane system, this rod and this beam. So, one can find the equivalent spring for this, equivalent spring for this one, and finally, as it is moving in this direction, as the mass is moving in the downward direction. So, one can find one equivalent stiffness of the system. So, this rod is subjected to axial force, then one can find the strain energy associated in this axial direction. So, one can find the strain energy here and for these two elements and then equate to that of the equivalent spring. Similarly, taking this rack and pinion system, one can find the equivalent mass. So, one may convert this rack and pinion to an equivalent rotating system. So, in that case, at this pitch point the velocity is, so if r is the radius of this pinion, then so r theta dot will be the velocity at this pitch point for this pinion, and for the rack it is the x dot, it is the translational motion, that is x dot. So, at pitch point the velocity is same. So, one can write this x dot r theta dot equal to x dot, or this is capital R. So, r theta dot equal to x dot, or one can write theta dot equal to x dot by r. So, now one can find the equivalent system. So, in this case the kinetic energy associated with this pinion equal to half j into theta dot square, and for this rack one can write this is equal to half m x dot square. So, for this equivalent system, if it is translatory, then I can write half m e into x dot square equal to half m x dot square plus half j into x dot by r whole square. So, the equivalent mass becomes m plus j by r square. Similarly, one can convert this whole system to an equivalent translatory system. So, in that case, in case of equivalent translatory system, the mass is this. In case of equivalent rotary system, one can find the inertia associated with the system. So, equivalent inertia equal to j plus mr square. So, similarly, by equating the dissipation energy, one can find the equivalent damping or equivalent viscous damping of the system. For example, in case of Coulomb damping, so if one draw the force versus x dot, then so this is minus mu n, this is mu n. So, in case of Coulomb damping, the force can be defined as F equal to mu n signum x dot. So, if the motion is harmonic, let x is harmonic. So, let x is harmonic. So, in this case x dot, so this is x versus time. So, x dot one can find x dot is cos. So, if x is in sine form, then x dot will be in cos form, x dot versus t. So, one can see it changes sign 2 times in this in one period. So, due to this change in direction of the velocity, so the force will change from minus mu n to plus mu n. So, due to this change in minus mu n to plus mu n, the system is not linear. So, the system may be considered to be nonlinear, or this damping one can write as a nonlinear damping. But one can find the equivalent viscous damping for this system. So, in that case the equivalent viscous damping will be equal to 4 mu n by pi omega x. So, this thing one can obtain by finding the energy dissipation due to this Coulomb force, and one can find that energy dissipation. So, for this portion of this motion, so this is, so if I am assuming x to be x sin omega t, then this is mu n or f up to x, then from here to here, So, this is minus mu n. So, this length is 2x. So, this is 2x, again for this portion the motion is n. So, the total area associated with this dissipation energy, total area equal to 4 mu x. So, this is mu n x, this is 2 mu n x and this is mu n x. So, total area or total dissipation energy becomes 4 mu n x. So, this dissipation energy one can equate with the equivalent dissipation energy for an equivalent viscous damper, and one can find this equivalent viscous damping. So, in this way one can find the equivalent systems, equivalent mass, equivalent stiffness and equivalent damping of the system. After finding the equivalent system or before going for the system, one can model or assume how to model the system. So, one may convert the system as a single degree of freedom system, it may be a 2 degree of freedom system, multi degree of freedom system or continuous system. So, let us review the linear single, multi degree of freedom system and continuous system. So, a linear single degree of freedom system can be represented by a spring, mass and a damper. So, if it is subjected to a force F sin omega t harmonic force, so then the equation of motion can be written in this form mx double dot, this is inertia force, cx dot damping force and kx stiffness force equal to the external force. So, one can find the response. So, the response will contain two parts, one is the transient part and the second part is the steady state part. So, the transient part will die due to the presence of damping. So, if it is due to damping and the steady state part will remain. So, the total solution of the system equal to x1 e to the power minus zeta omega n t sin 1 minus zeta square omega n t plus psi plus f by root over k minus m omega square. So, this is small m omega square whole square plus c omega whole square. So, in this case the first part is the transient part and the second part is the steady state response of the system. So, the transient part, so this x1 and psi depend on the initial condition and phi is the phase difference. This phase difference is will give the time lag or the time after which the response will occur when a force is applied to the system. So, we can have a rotating system, the force we have applied in this system depending on different systems, this force can be modeled in different ways. For example, in case of a rotating unbalance, so due to the presence of a small rotating mass, it will be subjected to a centrifugal force. So, the centrifugal force can be divided into two parts, one in vertical direction, one in horizontal direction. The vertical component will be me omega square sin omega t and this horizontal part will be me omega square cos omega t. But as it is restrained in this horizontal direction, so it can move only in the vertical direction. So, the vertical force me omega square sin omega t is the unbalanced force or is the force resulting force acting on the system in this vertical direction. So, due to that the system will be subjected to a vibration and one can have the response of the system, one can study the response of the system. Similarly, one can study the wheeling of a shaft. So, due to a bent shaft or due to the presence of an eccentric mass in the disc, the system is subjected to a centrifugal force. So, the plane containing the shaft axis and the bearing line will rotate with increase in the speed of the shaft. So, that will cause wheeling of the shaft. So, this wheeling of the shaft is a transverse vibration of the system. So, in this case one can find this r that is the distance from the center of this bearing center to the shaft center, r by E in this form, and if one plot that thing, then one can see. So, this is the phase angle versus frequency response. So, one can have the r by E response also. Also in this linear system one may study the support motion. In most of the cases, for example, in case of a vehicle moving on a wavy road, vehicle is moving on a road. So, generally there is undulation in the road. So, this road can be modeled as a vibrating or support vibrating vibration of the support. So, this vibration can be modeled as a periodic. For simplicity, it can be modeled as a periodic motion y equal to y sin omega t. So, due to this motion, so the instrument or the vehicle will undergo vibration, and the motion transmitted to the body due to the support motion can be given by this equation. So, in this case, if one plot x by y versus this frequency ratio, then one can observe that with increase in frequency of the support, initially the response increases. If there is no damping in the system, then that amplitude becomes infinity, but due to the presence of damping, the response reduces. One can observe irrespective of damping, the response, one can have the response equal to x by y equal to 1 at omega by omega n equal to root 2. So, this value is omega by omega n equal to root 2. So, after root 2 one can observe with increase in damping the response amplitude increases. Also one may observe in this case when one operates the system at a frequency very away from the natural frequency, then the phase angle is phi, phase angle phi equal to 180 degree, and irrespective of damping at omega equal to omega n, the phase difference equal to pi by 2. So, in case of support motion, like in case of support motion, the support is giving a force or motion to the main system. Similarly, a force can be transmitted from the machine, vibrating machine, to the ground. So, that force transmitted to the ground or the force transmitted to the machine can be isolated by using the principle of vibration isolation. So, the force, if one calculate how much force is transmitted to the ground, so this force is transmitted through the spring and damper. So, one can find the force transmitted to the support equal to root over k x whole square plus c omega x whole square. So, that is equal to k x root over 1 plus 2 zeta omega by omega n whole square. So, the amplitude of steady state response as it is known to be f0 by k. So, where f0 equal to amplitude of this force. So, a force of f sin omega f0 sin omega t is applied to the equipment. So, this x amplitude equal to f0 by k root over 1 minus omega by omega n whole square plus 2 zeta omega by omega n whole square. So, one can find the expression for force transmitted to the ground by the force of the machine, amplitude of the force of the external force. So, the expression is same as that we have seen in case of support motion. So, this x by y or ft by f0, one can get same curve. So, one can isolate the vibration of the system if it is operated at a frequency higher than root 2, and in that case one may observe when it is operating at a speed greater than root 2 times the natural frequency, presence of damping will increase the amplitude of the motion. And before omega, or if omega is less than the natural frequency, omega is the external frequency. If the external frequency is less than the natural frequency of the system, then a damper is a must. So, if there is no damping, so when one increase the frequency of the system, so it reaches a frequency, it reaches a very high value of amplitude. It may be infinity at omega equal to omega n if there is no damping present in the system. So, one can obtain the damping of the system by studying the sharpness of resonance. So, in this case one can see, in case of a single degree of freedom system, the maximum amplitude equal to 1 by 2 zeta. So, one can find the quality factor associated with this, and one can determine the damping of the system. Also, one may obtain the damping of the system from the free vibration of the system. For example, in case, so if one takes the free vibration response of the system, so in that case by plotting the response of the system, so if this is a underdamped system, then the response amplitude can be, will go on decreasing, and one can find different amplitude. So, this amplitude one can find. So, by dividing, let this is x1, this is x2, then this x2 by, or x1 by x2, ln of x1 by x2 equal to 2 pi zeta by root over 1 minus zeta square. So, this is known as logarithmic decrement. So, from experiment one can find the damping of the system by finding the logarithmic decrement of the system. So, using one accelerometer or vibrometer, one can find the response of the free vibration response of the system. So, after getting the free vibration response, one can find the successive amplitude, and from that one can obtain the logarithmic decrement of the system. So, after getting logarithmic decrement of the system, so one can find damping of the system. So, if the damping is very small, so one can neglect this zeta square with respect to 1. So, one can write this logarithmic decrement equal to 2 pi zeta, and one can easily get zeta from that. Also, so from this time response one can find the time period. So, this time period, so one can find this omega d, that is damped natural frequency of the system, equal to 2 pi by t. So, if one get the time period of the system, then one can find this omega d. So, the natural frequency of the system as it is related to the damped natural frequency by the expression omega d equal to omega n into root over 1 minus zeta square. So, one can obtain omega n of the system. So, after getting the natural frequency, one can find the system parameter or system stiffness if mass of the system is known. So, from the vibration response of this linear system, so one can find or identify the system parameters. So, one may use this vibration measuring instruments, so which work on same principle as that of the support motion to manufacture this vibration measuring instrument. So, recalling this x by y or z by y, z is the relative motion. So, one can use the same system as a accelerometer when it is operating at a very low frequency, and use as a seismometer when it is operated at a very high frequency. So, today class, so we have studied about the, or we have reviewed the linear system. We know different types of nonlinear systems, and also we have seen the application of the course, that is the nonlinear vibration system, to a range of systems. So, this course will be useful for the senior undergraduate or postgraduate students in mechanical engineering department, civil structural or aerospace engineering department. So, in the next class we will see the difference between linear and nonlinear systems, and we will also study the different phenomena associated with the nonlinear system.